In this lecture, I am going to present what is kinematic method and how to determine the collapse load of the simply supported beam, propped cantilever beam and fixed beam by kinematic method. First, coming to the kinematic method. This method starts with an assumed collapse mechanism. After collapse mechanism is found, there can be no change of curvature at any cross section except where plastic hinges are found. Hence, if a virtual displacement is given to the structure just after collapse mechanism is found, the internal work is done only at plastic hinge where plastic moment MP is acting. The collapse load is determined by equating the internal work done by plastic moment at plastic hinge to external work done by loads. In this method, all the possible mechanisms can be investigated and the one giving least value may be considered as real collapse load. If the bending moment is equal to or within the plastic moment capacity of the section at all sections, that is the real collapse mechanism, and the collapse load corresponding to this collapse mechanism is called the real collapse load. This method is also known as mechanism method or virtual work method. Then coming to the application of kinematic method to beams. For any span of a beam for collapse, there should be mechanical hinge or plastic hinge at the support and one plastic hinge in the span of the beam. To reduce the number of trial mechanisms, the point of maximum moment in the span of the beam should be identified. For a set of concentrated loads, maximum moment is always under a loads. In the case of simply supported beam, only one plastic hinge is found in the span of the beam. In the case of propped cantilever beam, one negative plastic hinge is found at the fixed end and another plastic hinge is found in the span under one of the load point. And in the case of fixed beam and subjected to transverse loading, the three plastic hinges are found. Two plastic hinges found at the two ends, and that is the negative plastic hinge. Two ends of the beams are the critical section where negative plastic hinges are found, and the third plastic hinge found in the span under one of the load points. This is the positive plastic hinge. And in the case of continuous beam subjected to transverse loading, each span can form a collapse mechanism on its own independent of the others. So you have to find out the collapse load for each span by considering the each span as a collapse mechanism. So you have to find out the collapse load from the each span, and the least collapse load is the real collapse load of the structure. So in the case of continuous beam, the minimum number of collapse mechanisms is equal to the number of spans. Then coming to the first problem, determine the collapse load WC in the simply supported beam shown in figure by kinematic method. So this is the simply supported beam. Support A and B are both simply supported, and the load W is present at the point C, that is at a distance small a from the support A and small b from the support B, and the length of the span is L. So in the case of simply supported beam, the bending moment is maximum under the load. So the interior hinge will be formed under the load. This is the figure showing the collapse mechanism. So this is the virtual displacement at the load point. Let theta 1 and theta 2 be the rotation of the portion AC and CB. There is only one plastic hinge found under the loading point at the C. The rotation at this hinge is equal to theta 1 plus theta 2. If this is the rotation at the support A theta 1, so this angle is also theta 1, and at the support B the rotation is theta 2. So here also this angle is theta 2. So what is the total rotation takes place at the plastic hinge C? That is equal to theta 1 plus theta 2. There is only one plastic hinge and rotation at this hinge theta 1 plus theta 2. Now from the geometry of the collapse mechanism, here we know this is the length A and this is the length B and the total length is L, and this angle is theta and this angle is theta, and this is the virtual displacement at the point C. So the delta is equal to A theta 1 is equal to B theta 2. The virtual displacement is equal to A into theta 1 is equal to B into theta 2. Now from the geometry, A theta 1 is equal to delta is equal to B theta 2. Then from this relation, theta 2 is equal to A by B into theta 1. Then find out the internal work done of the simply supported beam. So here we can find out the internal work done from the rotation and the plastic moment. So here only one plastic hinge found at the loading point C. So here the plastic moment is equal to MP. The internal work done is equal to MP into theta 1 plus theta 2. What is the total rotation takes place at the point C? That is equal to theta 1 plus theta 2, and the internal work done by this plastic hinge is equal to MP into theta 1 plus theta 2. Then after putting the value of theta 2 here, the internal work done is equal to MP is equal to theta 1 plus A by B into theta 1. Then after simplification, MP into B plus A by B into theta 1, but we know B plus A is equal to L, length of the span. B plus A plus B is equal to length of the span. So here you have to put this length. Then the internal work done is equal to MP into L by B into theta 1. So this is the internal work done. We can find out the external work done from the external load and what is the virtual displacement. The multiplication of the collapse load and the virtual displacement is equal to the external work done. So the external work done is equal to WC into delta. WC is the collapse load, the load which is acting at the point C, WC. So we have to find out WC. So external work done is equal to the collapse load into the virtual displacement at the point C. But we know delta is equal to A theta 1 is equal to B theta 2. So we have to put here in the place of delta A theta 1. So the external work done is equal to WC into A theta 1. Here the collapse load can be found out by equating the external work done with the internal work done. We know here the internal work done is equal to MP into L by B theta 1, and we know the external work done is equal to WC into A theta 1. So WC into A theta 1 is equal to MP L by B into theta 1. Then from this relation here we get the collapse load WC is equal to L by AB into MP. This is the collapse load of the simply supported beam when the load is present at a distance small a from the support A and small b from the support B. Then for particular case, if the load is present at the midpoint of the simply supported beam, then that case the A is equal to B is equal to L by 2, and after putting this value here in the place of A and B. So here we can find out WC is equal to L by 2 into L by 2 into MP. Then after simplification, the collapse load WC is equal to 4 MP by L. So this is the collapse load when the load is present at the midpoint of the simply supported beam, and this is the collapse load when the load is present at a distance small a from the support A and small b from the support B. For eccentrical loading, this is the collapse load. Then coming to the second problem, determine the collapse load WC in a propped cantilever beam of span L subjected to a central concentrated load W as shown in figure by kinematic method. So here we have to find out what is the collapse load of this propped cantilever by kinematic method. So here the load is given central concentrated load. This is the length of the propped cantilever L, and the load is given just at the midpoint of the propped cantilever. This is the prop and this is the fixed end. This beam develops collapse mechanism when plastic hinge is found at the fixed end and another hinge is under the loading point as shown in figure 2b. So this case, in the case of propped cantilever, one plastic hinge is found at the fixed end and another plastic hinge is found under the load point. Two plastic hinges found in this case. One negative plastic hinge is found at the fixed end and one positive plastic hinge is found just below the load point. So one hinge is found at the fixed end A and another is found at the point C. So this is the negative plastic hinge and this is the positive plastic hinge. And here load is present at the midpoint of the propped cantilever. Rotation at the end A and B both are equal. Rotation at the end A and rotation at the end B is equal to theta. Let the virtual displacement delta be given at the central hinge. Since the hinge is at the midspan, the rotation at the two ends are equal, that is equal to theta. Then the internal work done that we can find out by taking one plastic hinge at the point A and the second plastic hinge at the point C. From this plastic hinge we can find out what is the internal work done. So the internal work done is equal to MP into theta and at the point C MP into 2 theta. So the total internal work done is equal to MP theta plus MP into 2 theta. This is equal to 3 MP theta. Then the external work done can be find out what is the load is present on the propped cantilever, the load and the corresponding virtual displacement is equal to the external work done. The external work done can be find out in the case of propped cantilever beam, what is the load is present into the virtual displacement WC into delta. But we know delta is equal to L by 2 into theta. So this case, so this is the delta. So this is L by 2 and this angle is theta. So delta is equal to L by 2 into theta. Here after putting the delta L by 2 into theta, so the external work done is equal to WC into L by 2 into theta. This is the external work done. Then we can find out the collapse load by equating the internal work done to the external work done. That is, internal work done is equal to the external work done. So here we know internal work done is equal to 3 MP theta and the external work done is equal to WC into L by 2 into theta. Then after equating these two expressions, the collapse load is equal to WC is equal to 6 MP divided by L. So this is the collapse load of the propped cantilever, and when the load is present at the midpoint of the propped cantilever. Then coming to the third problem, find the collapse load by kinematic method in a fixed beam of span L carrying uniformly distributed load W per unit length over the entire span. The plastic moment capacity is MP throughout. So here the plastic moment capacity of this beam is MP, and this is the span of the fixed beam L, and this is the uniform distributed load W per unit length. The support A is fixed and support B is fixed. This is fixed beam with uniform distributed load. So in this case, there are 3 plastic is found. That is, 2 plastic is found at the 2 fixed end, and the 3rd plastic is found under the loading in the span AB. This beam develops collapse mechanism when plastic hinge is found at fixed end and another hinge is at the mid span, where positive moment is maximum as shown in figure 3b. So this case, the 2 plastic hinge is found at the 2 fixed end and the 3rd plastic is found at the mid span of the beam, where the positive moment is maximum. So this is the collapse mechanism of this fixed beam. This is the fixed beam with UDL, and this is the collapse mechanism of the fixed beam. So here 3 plastic hinges is found. The first plastic hinge is found at the support A, second plastic hinge is found at the support B, and the 3rd plastic hinge is found at the point C. As the loading is uniform distributed load, let the virtual displacement delta be given at the central hinge. This is the central hinge, positive plastic hinge, and this is the negative plastic hinge delta. Since the hinge is at the mid span, the rotation at both ends are equal. Because at the support A and support B, the same rotation takes place at the hinge is at the mid span. So this rotation is equal to theta, and this rotation is also equal to theta. If this is theta, then this is also theta, and this theta, this is also theta. So at the central hinge, the total rotation takes place 2 theta. So what is the internal work done by this rotation and the plastic moment? Then we can find out what is the internal work done by plastic moment and rotation. So here the plastic moment is MP and the rotation is theta. Here the internal work done is equal to MP into theta. And in the central hinge, the plastic moment is MP and the rotation takes place 2 theta. So MP into 2 theta. And at B, and at plastic hinge B, the plastic moment is MP and the rotation takes place theta. So the internal work done is equal to MP into theta. So the total internal work done, MP into theta plus MP into theta plus theta plus MP into theta. So this is equal to 4 MP theta. Then find out the external work done. The external work done can be found out by taking the total load into the average distance moved. The total load is equal to WC into L. And here this is the virtual displacement. This is the virtual displacement delta. So what is the average virtual displacement? This is equal to delta by 2. So the total load WC into L and the average distance moved, this is equal to the virtual displacement divided by 2. So this is the external work done in the case of fixed beam with uniform distributed load. So the external work done is equal to WC into L into delta by 2. But we know delta is equal to L by 2 into theta. So this case, this is the delta is equal to L by 2 into theta. L by 2 into theta. Here after putting delta is equal to L by 2 theta, the expression becomes the external work done is equal to WC L square by 4 into theta. Then the collapse load can be determined by equating the external work done with the internal work done. So the external work done, this is equal to WC L square by 4 into theta, and here we know the internal work done is equal to 4 MP into theta. Then after simplification, the collapse load is equal to WC. So this is equal to 16 MP divided by L square. So this is the collapse load of the fixed beam subjected to the uniform distributed load. Then coming to the fourth problem, determine the collapse load in a fixed beam shown in figure by kinematic method. So this is the fixed beam. So here there are present two load. One load is at the point C and another load is at the point D. The first load is 1.25 W that is present at C, and the second load W that is present at D. And the first load present at C 1.25 W at a distance 0.2 L from the support A, and the second load W which is present at D at a distance 0.25 L from the support B, and the total length of the fixed beam is L. So this is the fixed beam with 2-point loads. So in this case, at the collapse mechanism, hinge will be formed at supports and another hinge in the span. In the case of fixed beam, at collapse mechanism, so two hinge will be formed at two supports and another hinge will be formed in the span. So the interior hinge may develop under 1.25 W load or under load W. The interior hinge may develop under this load or under this load, that is under the load 1.25 W or under the load W. Hence this case we have to analyze by considering both the mechanism. The first mechanism we have to consider, that is the two hinge at the two support and one hinge is at this load point, and the second mechanism we have to take two hinge at two supports and the third hinge that is under the load point D. Hence both the mechanism will be investigated, and which is giving the less collapse load will be selected as the real collapse mechanism subjected to the load 1.25 W and W. So first we will take the mechanism 1. So in mechanism 1, so here we will consider two plastic hinge at support A and support B, and the third plastic hinge is at the point C under a load 1.25 W. This is the first collapse mechanism. We have to take two plastic hinge at two support A and B, and the third hinge which is under the load 1.25 W. This is the third hinge. And the rotation at the A is theta 1 and the rotation at B is theta 2. And delta 1 is the virtual displacement under the load 1.25 W, and delta 2 is the virtual displacement under the load W. Here the virtual displacement is at delta 1 under the load 1.25 W, and under the load W the virtual displacement is equal to delta 2. And theta 1 and theta 2 be the rotation at the ends A and B. So if this is theta 1 and this angle is also theta 1, and if this is theta 2 and this angle is also theta 2. So here first we will find out what is the relation between the theta 1 and theta 2 and delta 1 with the theta 1. Let us take two similar triangle here. This is one triangle, this is one triangle, and this is the second triangle. Two similar triangle. So delta 1 and this length is equal to 0.8 L. From this to this is 0.8 L, and from this to this is 0.25 L, and this is delta 1 and this is delta 2. And consider these two similar triangle, and from these two similar triangle we can find out what is the relationship between the delta 1 and delta 2. So delta 1 divided by 0.8 L is equal to delta 2 divided by 0.25 L. Then from this relation delta 2 is equal to 0.25 L by 0.8 L into delta 1. This is the equation 1. Then from this collapse mechanism, here this angle is theta 1 and this length is 0.2 L. So 0.2 L theta 1 is equal to delta 1 is equal to, from this to this length is 0.8 L and this angle is theta 2. 0.8 L into theta 2 is equal to delta 1. So here this relation is 0.2 L theta 1 is equal to delta 1 is equal to 0.8 L theta 2. This one 0.2 L theta 1 is equal to delta 1 is equal to 0.8 L into theta 2. And from this relation here we get theta 1 is equal to 4 theta 2. So this is equation 2. Then find out the internal work done. The internal work done can be find out what is the plastic moment here mp and what is the rotation takes place theta 1. The internal work done at A is equal to mp into theta 1. Similarly, what is the internal work done at C at this hinge? So here the total rotation takes place theta 1 plus theta 2 and the plastic moment is equal to mp. So here the internal work done is equal to mp into theta 1 plus theta 2. And what is the internal work done at B, at the plastic hinge B? So here the plastic moment capacity is mp and the rotation is theta 2. So the internal work done at the plastic hinge B is equal to mp into theta 2. Then what is the total internal work done from these three plastic hinge? Mp into theta 1 plus mp into theta 1 plus theta 2 plus mp into theta 2. Then after simplification, internal work done is equal to 2 mp theta 1 plus theta 2. But here we know theta 1 is equal to 4 theta 2. So after putting the theta 1 value here, 4 theta 2, the internal work done is equal to 10 mp into theta 2. Then find out the external work done. So the external work done, here the load is present 1.25 W, WC. For collapse load, we have to take WC, 1.25 into WC. And here the load is WC. What is the external work done is takes place due to this load? 1.25 WC into delta 1. And what is the external work done due to this load? WC into delta 2. What is the total external work done due to the both loads? The total external work done is equal to 1.25 WC into delta 1 plus WC into delta 2. External work done is equal to 1.25 WC into delta 1 plus WC into delta 2. Then external work done is equal to 1.25 WC into delta 1 plus WC into, but we know here the delta 2 value, delta 2 is equal to 0.25 L by 0.8 L into delta 1. So put this delta 2 value here, 0.25 L by 0.8 L into delta 1. Then after taking the common WC into delta 1, the external work done is equal to 1.25 plus WC delta 1 into 1.25 plus 0.25 by 0.8. Then after simplification, the external work done is equal to WC into 1.25 into L into theta 2. So this is the external work done. Then find out the collapse load by equating the internal work done with external work done. So here we know the internal work done is equal to 10 mp into theta 2 and the external work done is equal to WC into 1.25 into L theta 2. So equate these two, internal work done and external work done, and from this relation we have the collapse load WC is equal to 8 mp divided by L. So this is the collapse load from the mechanism 1. From this mechanism, the collapse load is equal to 8 mp divided by L. Then consider the mechanism 2. So in mechanism 2, you have to take the plastic hinge just below the load W and another two plastic hinges are the two supports, are the two fixed end. We have to consider the internal hinge under the load point W at D and the two negative plastic hinges at the fixed end A and B. So this is the second collapse mechanism. The internal hinge developed under the load W from the default shape, from this shape. So here this is the virtual displacement at D under the load W, and this is the virtual displacement delta 1 under the load 1.25 W. Here this rotation is theta 1 and this rotation is theta 2, and at the plastic hinge D the rotation is theta 1 plus theta 2. Then by considering these two triangles, similar triangle, here also you have to consider two similar triangle. This is one triangle and this is another triangle, and from these two triangle we can find out the relationship between the delta 1 and delta 2. Here we know the length is 0.12 and this virtual displacement is delta 1, and this length is 0.75 L, and this virtual displacement is delta 2. So delta 2 by 0.75 L is equal to delta 1 divided by 0.2 L, this one. Then from this relation here we get delta 1 is equal to 0.2 divided by 0.75 into delta 2. This is the relation between the delta 1 and delta 2. Then here we know this is theta 1 and this is theta 2. So here, and this length is 0.75 L and this length is 0.25 L. So 0.75 L into theta 1 is equal to 0.25 L into theta 2 is equal to delta 2. So here 0.75 L into theta 1 is equal to delta 2 is equal to 0.25 L into theta 2. From this relation we get theta 2 is equal to 3 theta 1. So this is equation 7 and this one is equation 6. You can find out the internal work done from this collapse mechanism. The plastic is at A, the plastic moment is MP and the rotation is theta 1. So what is the internal work done? MP into theta 1. And at the plastic hinge B, the plastic moment MP and the rotation theta 2. What is the internal work done? MP into theta 2. And at the plastic hinge D, the total rotation takes place theta 1 plus theta 2 and the moment is MP. So what is the internal work done? MP into theta 1 plus theta 2. So the total internal work done is equal to MP into theta 1 plus MP into theta 1 plus theta 2 plus MP into theta 2. This one. Then after simplification, this is 2 MP theta 1 plus theta 2, but here we know the relation between the theta 1 and theta 2. After putting the theta 2 here, we get 2 MP theta 1 plus 3 theta 1. Then after simplification, internal work done is equal to 8 MP into theta 1. Then find out the external work done. So here the load is present 1.25 W and here this is the virtual displacement. So what is the external work done by this load? 1.25 WC into delta 1. And what is the external work done due to this load? WC into delta 2. So then what is the total external work done? 1.25 WC into delta 1 plus WC into delta 2. 1.25 WC into delta 1 plus WC into delta 2. Then the external work done is equal to 1.25 WC, but here we know what is the relation between the delta 1 and delta 2. This is delta 1 is equal to 0.2 by 0.75 into delta 2. So here you have to put this delta 1. So here you have to put the delta 1 0.2 by 0.75 into delta 2, then plus WC into delta 2. So the external work done is equal to 1.25 WC 0.2 by 0.75 into delta 2 plus WC into delta 2. Then after taking the common WC into delta 2, the external work done is equal to WC delta 2 1.25 into 0.2 by 0.75 plus 1. Then after simplification, the external work done is equal to WC into L into theta 1. Then the collapse load can be determined by equating the internal work done to the external work done. So internal work done is equal to external work done. So here we know internal work done is equal to 8 MP into theta 1 and the external work done is equal to WC into L theta 1. So from this relation here we get the collapse load WC is equal to 8 MP divided by L. This is equation 10. So from the mechanism 1 we get the collapse load, this is 8 MP by L. From the mechanism 2 also we got the collapse load is equal to 8 MP divided by L. So from the both the mechanism we got the same collapse load. So both mechanisms give the same collapse load, hence two mechanism occurs simultaneously. Here from the mechanism 1 we got the collapse load 8 MP by L, and from the mechanism 2 we got the collapse load 8 MP by L. So both mechanisms give the same collapse load, hence the two mechanisms occur simultaneously, and the collapse load of this beam is equal to 8 MP divided by L. Now all are clear how to find out the collapse load of simply supported beam, prop to cantilever beam and fixed beam by kinematic method.